So let's begin lecture 21 on Lagrange multipliers. Actually, it's a little bit more than that because to start with, I need to talk about the problem that we're now facing in this course. And the problem is this: we're given some function and some space S. The question is, how can we find the minimum or maximum of the values of the function attained from inputs taken from that space? All right. So in particular, as we think about a space, there's kind of two cases to consider, right? That space, it has an interior part, all right, and it also has an edge, generally speaking. You could think about it having an edge or a boundary. And so the way we find minimum and maximum of a function in those two different cases, the inside or the edge, it's rather different. And it turns out Lagrange multipliers is one of the methods we can use to examine, how the function has minimum or maximum on the edge. In particular, the dimension of S is the dimension of the interior, and that's going to be one more than the dimension of the edge. So if S is a surface, then the boundary of S is a curve. If S is a volume, then the boundary of S is a surface. And in this lecture, we'll share techniques to study the extremal values on the boundary of S when either the boundary of S is either a level curve or level function. But I should mention, looking ahead, to maximize a function, we have two steps, right? The one is to look for extrema in the interior. We'll find critical points. That's places where the gradient is 0, or where it doesn't exist, or there's a discontinuity in the function, whatever. And those give us candidates for minimums or maximums. Of course, we could also look at the Hessian at such points to clarify the nature of the critical points as min, max, or saddle. That'll be the topic of a future lecture. And then on the other hand, to find extrema on the boundary of S, we either can parameterize the edge and look at the function restricted to the edge, which gives us a function of one variable. We can drop back to Calc 1 and use chain rule for functions of several variables paired with the min-max theory from just calculus of one variable on that, or we can use the method of Lagrange multipliers. All right. So this lecture basically is going to go through, hit the high points on page 231 to 245 of the 2020 lecture notes. So let's get to it. So first of all, I owe you at least a brief mention of the definition. What do we mean by local maximum, local minimum? It's just what it sounds like, right? It's a local maximum if the values of the function are smaller than that maximum close to the point, and likewise vice versa for the minimum. You can also talk about global maximum, minimum. That would mean that it's the largest value the function takes everywhere, or the smallest it takes everywhere. And excuse me. So let's get straight into it. What is the method of Lagrange multipliers? Well, so here it is. I'll find my cover sheet. So this is the method of Lagrange multipliers. For some smooth functions, f and g, with non-vanishing gradients on g equal to 0. So g equals to 0 is the so-called constraint equation. All right, so there's a more general version of Lagrange multipliers where the constraint, they could have more than one constraint equation. You could have several. But I'm not going to talk about that in here. If you want to see more on that, you can look at my advanced calculus class from previous years. I sometimes cover that, but it is part of like the general story of normal spaces and tangent spaces and such. But anyway, here f is the objective function. So our objective is to make that function as big or small as possible. Objective function is what it's usually called. All right. And the method of Lagrange multipliers says, hey, if you want to find places where the objective function is largest on the constraint equation holding true, you look to solve this equation right here, that the gradient of f is equal to lambda times the gradient of g. And here lambda is the so-called Lagrange multiplier. And so this is a system of equations relating the partial derivatives of f and the partial derivatives of g. And we're also, of course, insisting that g equals to 0. That's part of the story here. So let's talk about this idea. So notice that the method does not provide the existence of the maximums or minimums. It only gives you, you know, a best guess, right? Like these are places where it might happen. Okay, so and we'll see examples that show when g equals to 0 is a closed and bounded set, then the extrema for f do exist. That's part of a theorem from analysis, right? If we have a continuous function with a closed bounded domain, then the extreme value theorem says that the maximum minimum is attained for some point in the set. But more generally, if you just have a constraint surface or a constraint curve, which is not compact, which is not closed and bounded, anything can happen. All right, anything can happen. And Lagrange multipliers solutions can be misleading. I'll try to show you some examples of that. But first, a proof of the method. So, and here's the n equals 2 proof. So, let me zoom out just a bit. All right. So suppose f has a, come on, where we go? Suppose f has a local maximum at x0, y0 on the curve g of x, y equal to 0. And then we can let I be an interval containing 0, which parameterizes the curve, so g of r of t is equal to 0. If that defines h, if h is the composite of well, that doesn't define h, but if f is f composed with r is the h function, then it should have a maximum at t equals to 0, because we've made t equals to 0 where the point given is. Anyway, so if that is a maximum of a function of one variable, then of course the derivative should be 0 there, right? And so, on the other hand, we have the chain rule, right? So the derivative of f composed with r is gradient of f dot dr dt, right? But on the other hand, we also know that g is identically 0, so we can differentiate that and get the gradient of g dot dr dt equal to 0. So we're in 2 dimensions, right? And so if you think about it, here's the curve, g equals to 0, right? This is the point we're studying where we have a maximum attained for f, the objective function, right? And if you think about these two equations, well, this is the tangent vector, right? dr dt. Right? It's tangent to the constraint curve g equal to 0. And we have that the gradient of f and the gradient of g are both what? They're both perpendicular, right? So what does that mean? That means that the gradient of f is either got to point this away or that away, right? I mean, I'll just say this. Maybe this is the gradient of g. Maybe this is the gradient of f. I wouldn't know without more details. But the point is they have to be collinear because they're both perpendicular to the velocity. And as such, that means that we can set, the gradient of f equal to some multiple, which we call lambda of the gradient of g. And that, my friends, is the method of Lagrange multipliers, that we can look for the gradient of the objective function being a multiple of the gradient of the constraint function. So, all right. Now, moving along here, I also have a proof in the n equals 3 case, which I think is in some sense more interesting. Pretty much all our examples would either be in 2 or 3 dimensions. So I'll draw the picture in n equals 3. Basically, what goes on here, n equals 3, is instead of having a level curve for the constraint, we have some kind of constraint surface, right? And so maybe that defines g equals to 0, right? And we know that the gradient of g is normal to that surface, right? So suppose that suppose at that point right there, your objective function, oh man, hello?
Hello, can you hear me, James?
Yeah, see?
Hello, James. My name is Tammy. I'm calling from QNet and the truck. How are you?
From what?
From QNet and the truck.
Oh, yes, yes.
I just want to confirm the move tomorrow.
Yes, the 10, between 10 and 10:30, is that right?
Yeah. They should be right on time at 10 o'clock at 202 16th Street.
Okay.
And we'll give it 3 guys to get that date.
It's for a piano.
I'm so sorry. I just saw here that it weighs 100. If I put your count upright, and I didn't do it today. I'm sorry.
It might as well be a safe. It's miserable.
Okay, well, then we'll take care of it for you.
Yeah.
I apologize. I didn't look at the whole estimate, but they should be right there at 10 o'clock tomorrow.
Okay. Well, we'll be there waiting for him.
Okay,
All
thank
right.
you so much.
Thank you. Okay. Yeah. Bye bye. All right. Well, continuing. Sorry about that, guys. So I have movers coming to move my piano. You know, it's very exciting. Anyway, we just moved again. All right. So if that's the place where the objective function has its maximum, right? Then if we look at a curve, any curve you like through there, right? And you know, that curve is parameterized, so like this point would be, say, r of t, right? And we can parameterize the curve and put t equal to 0 at that point where the maximum is, right? And so once more, the the tangent vector to the curve on the constrained surface would look like that, right? And it's going to be, of course, it's going to be perpendicular, right, to the gradient of g. And the thing is, we can also argue by essentially the same calculation as the n equals 2 case that the gradient of f must also be perpendicular to the velocity vector, because again, f composed with r of t is a function of one variable which is maximized at t equal to 0, because that's where f is largest, or where f has an extreme value at that point, you know. So what do we got? We've got the gradient of f is perpendicular to the velocity. We've got the gradient of g is perpendicular to the velocity. And well, if that were just one curve, it could be possible that the gradient of f, you know, is not collinear with gradient of g, right? But I can do it for not just one curve. I can do it for a multitude of curves, right? I can do it for a bunch of different curves on the surface. And so if you start thinking about that, right, we get it also is perpendicular to that velocity vector, right? And it's perpendicular to all velocity vectors that form the tangent plane. So since the gradient of f is perpendicular to all velocity vectors, it must be that it's collinear with the normal vector, which is the gradient of g. And so again, we get the method of the Lagrange multiplier equation that, you know, gradient of f is equal to lambda times the gradient of g. All right, so that's why the method works. Let's see how it works. So here's some examples. So suppose I want to find the maximum and minimum distance to the origin for points on the curve x squared minus y squared equals to 1, right? So my objective is to make the distance from the origin small. So my objective function here, I let be f of xy equal to x squared plus y squared. That's my objective function, all right? Because we might as well make the squared distance as small as possible, right? You could work directly with the square root of x squared plus y squared, but why bother when the distance squared will also be maximized, or rather minimized, or minimized or maximized whenever the distance is minimized or maximized. All right, so our constraint function is x squared minus y squared equal to, you know, that's equal to 1. So gradient of f is 2x, 2y. Gradient of g is 2x minus 2y. We want to seek solutions of the Lagrange multiplier equation, which gives us 2x, 2y equal to lambda times 2x minus 2y. All right? And hence, 2x is lambda 2x, and 2y is minus 2 lambda times y, right? We have to solve this equation and that equation subject to the condition that, you know, x squared minus y squared is 1. So if you look at it, x equals to 0, would be one way you could solve that, right? But that's not a solution because that gives you, on the constraint equation, it gives you minus y squared equal to 1, which has no real solutions. But on the other hand, if we look at y equal to 0, that works because when we put y equal to 0 into the constraint equation, we get x is plus or minus 1. So looks like we need to have y equals to 0 and x equal to plus or minus 1, I think. But let's see here. So I'm like, all right, well, let's be more systematic. So what I did, right, and so this is a good strategy. You can reason through things like I was just reasoning through them, but it's better to trade these equations for something like these equations, because then you can kind of be more systematic, right? So this means either x is equal to 0 or lambda is equal to 1, right? So if you think about it, if x is equal to 0, that means lambda, so if x is equal to 0, that's not possible because of the constraint equation, right? So this means lambda must be 1, all right? So if lambda is 1, it must be that this is 2, and so 2y equal to 0, so that forces y to be 0, right? So in other words, 1, 0, and minus 1, 0, the ones I already found, that's it. Those are the solutions to the Lagrange multiplier problem. So I say in this case the method of Lagrange multipliers has served its purpose, right? As you can see in the left graph, below the green curves are the level curves of the objective function, whereas the particular red curve is the given constraint curve. Let's see if I can add the color to my handy-dandy graph from the next page here. All right. Sorry, I don't have a color printer at the moment, so I'm having to do some of this by hand. But you're like, why don't you figure out how to put things on a computer and talk while you're looking at your notes? I don't know. Let's see here. Because computers don't give me joy. Yeah, that's why, in a nutshell. Let's see here. Okay, so here's a picture. The constraint x squared minus y squared equal to 1 is this hyperbola. Right? That's x squared minus y squared equals to 1. So, all right, that's the constraint curve. And then these circles are level curves of the objective function x squared plus y squared equal to, well, right? So here's some level curves of the objective function. And so the method of Lagrange multipliers, the wisdom of it is that wherever the gradient of the objective function matches, it's collinear with the gradient of the constraint function, that's where you're going to find your like min or max, maybe. And of course that happens here at these points. In this case that's, well, 1, 0, and this guy over here minus 1, 0, right? And are those minimums or those maximums? Well, I think it's not hard to see that that's the minimum value. I mean, that's the closest distance to the origin for the red curve, right? So these are places, the distance is 1. So the distance is smallest at 1, and then there is no maximum, right? And that's okay. That doesn't violate the extreme value theorem here, because the constraint curve is not compact. It goes on and on, right? So we weren't really guaranteed that anything was a min or a max here. We're fortunate in that the method worked out. All right. Another example, and this is just a picture of the gradient vector field to the objective function and the constraint function. Here's another one. Suppose we wish to find the points on a circle. So I keep losing my cover sheet. Where'd it go? So suppose we wish to find the points on the unit circle. This time the unit circle is the objective function. and we're going to turn the table. We're going to let the, rather the unit circle is the constraint function, and this time the objective function is going to be x squared minus y squared, right? So it's kind of like the last example, but the formulas are flipped over in their application. So we look at the Lagrange multiplier equation. 2x minus 2y is gradient of f, and lambda times 2x 2y. And so as I was advertising last time, it's better to look at 2x equal to 2x as 2x lambda as 1 minus lambda times x, and the other one is also nicely written as 1 plus lambda times y, because then you have the product of things equal to 0, right? So you can easily cipher the cases. So like if lambda equals to 1, we solve that one, right? But then that forces y to be 0. And of course if y is 0, well, after this I'll say, okay, and if y is equal to 0, what is x equal to? Well, that means x squared, the constraint is x squared plus y squared, right? Equal to 1. So x squared plus 0 squared equals to 1. So this case gives me x is equal to plus or minus 1. And so this case 1 here gives me points plus or minus 1 and 0. So there's those 2 points. The next one, lambda equal to minus 1, well that takes care of this one. But then it leaves this as 2x equal to 0. So that forces x equal to 0. And then by the constraint equation, 0 squared plus y squared equals to 1, which is telling me that, well, y is equal to plus or minus 1. So that gives us the point 0 plus or minus 1. So far we've found four points that the Lagrange multiplier method gives us. And in fact, that's it, those 4 points. And we test the objective function at those 4 points to see what happens. And when you do it, you get minus 1 at 0 plus or minus 1, and you get 1 at plus or minus 1 comma 0. And so we find that when you constrain the objective function to the unit circle, you find a max of 1 at those 2 points and a minimum of value of minus 1 at 0, 1 and 0, minus 1. And I think I got a picture of this as well. Let's look at the picture. Oh. Come on. Come on. If my fingers would work. Here it is. So this time the constraint, which I'm doing in red at the moment, was the unit circle. And this family of hyperbolae, those are the level curves of the objective function, right? So I had g of xy equal x squared plus y squared equals to 1. And the objective function for this one I said was x squared minus y squared, I believe. Right? And we're looking, basically the search is find maximum and minimums for f on the g equal to 1, you know? And so when you look at some level curves, you'll notice that these guys, in particular, the ones that just kiss the red circle, like that, is where the gradient of the green curve matches the gradient of the red curve, and that's exactly what the Lagrange multiplier equations just derived for us, was that this point, this point, this point, this point, and this point, those are potential extremal points for f, subject to that unit circle. All right? And again, the reason that this worked out, the reason that we found the minimum, let's see here, I'm trying to remember. If I plug in 1, 0, I get the value 1 here, and I get the value 1 here, I get the value minus 1 up here, and minus 1 down there. So in fact, the max is 1 at plus or minus 1, 0, and the min is minus 1 at 0 plus or minus 1. It's attained at 2 places. And that had to happen here because this unit circle is an example of what's called a compact subset of R2, and a well-known theorem of analysis states that any real-valued continuous function on a compact domain attains both maximums and minimum values. This is the so-called extreme value theorem. All right, and extreme value theorem. And all right, so another example. Suppose we want to find, and this is a very silly example. I warned that in advance. Suppose we want to find the extrema of f of xy equal to x when constrained to xy equal to 1. So, okay, the method of Lagrange multipliers gives us that 1, 0 equals to lambda times yx, which tells me 1 is equal to lambda y and 0 is equal to lambda x. Now if lambda equals to 0, then 1 equal to lambda y is impossible. So we can assume that lambda is non-zero, and we find then that x must be 0. And if x is equal to 0, then xy equal to 1 is not solvable. Therefore, no solutions. All right, well, I guess I suppose I've succeeded here in a way. We've just learned that there's no extreme value of x on the hyperbola xy equal to 1. At least not according to the method of Lagrange multipliers. And is that true? Well, let me draw a picture. I mean, it's true, right? Here's the picture, the constraint xy equal to 1 is just the hyperbola that's, like this. That's xy equal to 1, which you're probably more conditioned to seeing that as y equals to 1 over x, but there it is. And of course, if you look at the level curves of the objective function, like these guys, right? Is there any smallest or largest value of x attained in the gradient? I mean, obtained in the level curve, the hyperbola, the red curve? No, I mean you can get as large or as small as you want in x, and okay, fine, I'll give it to it. The method of Lagrange multipliers was successful there in the non-answer. Great. Here's one where it's actually misleading. So find the extrema of f of xy equal to x again, this time constrained to the hyperbola x squared minus y squared equals to 1. So you apply the method of Lagrange multipliers, you go through the algebra, and the algebra suggests to you that either 1, 0 or minus 1, 0 are potential, potential min-maxes. And the constraint curve is this hyperbola, right? And what the method of Lagrange multipliers does is it does find the place where the gradient of the red curve, sorry, I'll scooch it up here a bit. It does find for you where the gradient of the red curve, matches the gradient of the, let me pull this out of back here a little bit. So again, the method of Lagrange multipliers led us to basically this one and that one as being the levels where the gradient for the green matches the gradient for the red, in particular at these points, this guy and that guy, right? 1, 0, and this one over here, minus 1, 0. And so you might be tempted then to think, oh, well, f of 1, 0 equal to x, which is 1, and over here f of minus 1, 0, which is equal to x, which is minus 1. So that must be the maximum, and that must be the minimum, value of the objective function subject to the constraint. And this is just not true, because x gets as large as you like over there, and x gets as negative as you like over there. The min and maximum of the objective function x do not exist on this curve, and that's because, well, I mean, why is this possible? Why didn't the method of Lagrange multipliers have to succeed here? Is that the constraint curve is not compact, so the extreme value theorem does not tell us anything. And so this is the thing: the method of Lagrange multipliers you can always apply for reasonably differentiable things, and you just have to use some common sense at the end of it. Is it actually a solution, or is it just wasting your time? This one just wasted our time. So, all right, let me stop wasting your time. Move on here. So I've got a bunch of examples in this section. I won't go through detail on all of them. Let's see here. I'll just kind of give you a summary of the example. This one here, the objective function, x squared plus 3y squared on the unit circle. So like this, the objective function here has ellipses, which are level curves, and the objective function, of course, is a unit circle, and so there's probably going to be like 4 points where those line up. Yeah, I get either 0 plus or minus 1 or plus or minus 1, 0 as the potential potential extremal points, and in fact the minimum is 1 and the maximum is 3 as it happens here. So and this one worked out because the objective function, excuse me, the constraint function g was a unit circle. All right, so yeah. Let's see here. It'd be fun to draw the picture for that one, but I'm going to go on. This one, find the closest point on the plane. Sorry, did I? Well, I'll let you read the notes. If I have scrolled past something and not put it in the video, my apologies. But, you know, I don't want to make these videos too long here either. So, I certainly don't have time to go through everything in the notes. But I think it might be useful for me just to tell you kind of a big picture of the example in the notes, and I can do that pretty quickly. So here, find the closest point on the plane, 2x minus 2y plus 6z equal to 12, to the point 2, 3, 4. Now, remember, we had another way to do this. We find the normal line through that point, and then find the intersection with the plane, and then that gives us the closest point. But here's another way. This time, the constraint function is 2x minus 2y plus 6z. Now, it's a level surface, not a level curve, right? And so g, this is g equals to 12, basically. I'm saying this is my g, quote unquote, as a function of x, y, and z. And the objective function is the distance squared function from the point 2, 3, 4 to the point x, y, z, which is just that. So this gives us the distance squared from x, y, z to 2, 3, 4. We want to make that as small as possible. And so Lagrange multiplier equations, gradient of f is lambda gradient of g, which gives us this lovely vector equation, which gives us 3 separate, component, the x component, the y component, the z component, get these 3 equations. And you can plug those into the plane equation. That gives you this thing, which gives you that, which eventually tells you that the Lagrange multiplier is minus 5/7. And so we deduce that the closest point is this, and there it is. Now, in this case, in some sense, we got lucky, right? Because if you think about the plane, right, which I'll draw as red because I've been making my constraint stuff red, right? So the plane is the constraint, right? And it goes on, right? It's not compact. And yet, Lagrange multiplier method, we applied it to the point 2, 3, 4, right? And we found that, we found that point here on the plane, which is closest, which is that one, right? And so basically, I'm advocating that common sense says that that is a solution, right? There is a point on the plane closest to a given point, right? I haven't proved that, but I think it's geometrically reasonable. It's also geometrically reasonable to see that there's no maximum here, right? Because you can always go further out the plane to get farther away from that point. So that's why it's kind of lopsided here. We did find a minimum value, but we didn't find a maximum value. That's because the extreme value theorem does not apply here because the constraint surface is not compact. It's not closed and bounded. All right. Another example. This one, the objective function is f of, let me zoom in a bit here. This time the objective function is e to the xy, and I want to find the extrema of f on the curve x cubed plus y cubed equal to 16. That's an interesting curve. It looks like this down here, actually. It is, so it's not compact, right? It goes on and on. It's kind of neat. There it is. There's the constraint curve. I'm not going to try to draw the level curves of e to the xy. I mean, I guess I could. Fine. What if you set e to the xy equal to a constant? What does that give you? If I take the log of that, I get xy equals to the natural log of c. So y is equal to, like, natural log of c over x. So, this is just I mean, the objective function has level curves, which are like, these kind of deals. Right, so there's just seems like there's going to be one that lines up there, right? So, I guess we could have natural log of c be negative 2, right? That would give us stuff over here, So here's some level curves for what it's worth. Anyway, so we calculate the gradient of the objective function, set it equal to lambda times the gradient of the constraint curve, gives us that. And so this time I decided to solve for lambda. I get this, but I also get that. So if you solve both equations, the x and y equations for lambda, it eliminates lambda, so at least you've got an equation with just x and y in it. And then you can cancel the e to the xy, and that gives us x cubed equal to y cubed. But then x cubed plus y cubed is 16, which gives us that 2x cubed is 16, so I get x is equal to the cube root of 8, which is about 2. So this, as you can see, this point right here is happening at 2. Cool. And e to the 4, and that's in fact global maximum of f of xy equal e to the xy. And so this claim is seen from examining the exponential function in each quadrant as the point gets further away from the origin on the constraint curve. So I'm not saying that it's immediately obvious that that's a global maximum, but it's a potential maximum or a potential minimum. And if you actually study what happens to the values numerically, you can see that in fact that is a global maximum. All right, because as I said, I mean, here's some of the numerics. In both quadrants 2 and 4, we have xy. Quadrant 2, quadrant 4, we have xy is less than 0, which means, of course, that e to the xy is less than 1. So the maximum found must happen up in here. Another way, excuse me. Another way you could look at this is you could take your constraint curve and divide it up into 3 pieces. Like this tail that goes off, that tail that goes off to infinity, or way out. And then there's this like little arc in the quadrant 1, And if you just focus your attention on that going from here to here, that is compact because you could put it in a little disk, it's closed and bounded, and you could find the minimum of the function on that piece. And then you could kind of like, look at those 3 different cases and put them together. And so there are things like this we could do, kind of divide and conquer strategies for problems. But anyway, I thought I should mention that because there's a lot of creative options here, and I know some of you guys are pretty creative, so I would say that there's a lot of things you might think of. But anyway, this one, the objective function is xyz, and the constraint surface is actually an ellipsoid, and so again, we get 3 Lagrange multiplier equations because it's a 3-dimensional problem, and so you can solve those through the algebra here, and when you do that, you get actually 8 potential winners or losers here, and those 8 points, when you evaluate them, give you these different values: 2 over root 3 or minus 2 over root 3. And so apparently 2 over root 3 is the maximum, and minus 2 over root 3 is the minimum. And it's attained at actually 4 points, and I actually have some pictures to illustrate how that happens. The ellipsoid is the constraint surface, and if you look at xyz equal to a constant, because that was the objective function here, f of xyz. equal to xyz. If you look at xyz equal to a constant, it gives you these kind of funky sheets that are, I don't know, like two-dimensional versions of the hyperbola function or something. I'm sure there's a name, I've forgotten it, but anyway, it makes sense that there's going to be these, like, you know, four minimums and four maximums when you start looking at the way the constraint surface, this ellipsoid, is going to touch up on those four sheets given by f of x, y, z equal to a constant. Why are there four sheets for f of x, y, z? Interesting. Anyway. And then here is another find the point on the plane closest to that point. I already did that example with a different number. Here it is again, this time with a picture. Woohoo! As you can see. And then finally a look, oh, an applied problem. I'll skip that. Ha ha ha. Just kidding. I mean, of course there's tons of applied problems you can do with Lagrange multipliers. Here's a popular one. A rectangular box is made without a lid. And from 12 square feet of cardboard, find the maximum volume of such a box. Well, so basically you're constrained by the surface area, 2xz plus 2yz plus xy equal to y, 12. The asymmetry here with xy is because, of course, making the picture something like this, right? Okay, so this is x. This is, you know, this is y. I'm labeling this point here as x, y, z, I think. And so, you know, it's open top, right? So there's just xy is the area of the bottom, right? Just this piece down here, and there's no top, so that's why there's just an xy here. Whereas yz, at the risk of cluttering my picture up, would be this right here. So there's that. And there's two of those because there's a front and a back face, right? And then, of course, there is also the other side, right, over here, which would have area xz. And you got two of those, so that's why you've got 2xz. You got 2yz. So there you go, that's the constraint. And the objective is to make the volume as big as possible, right? Or minimize it. What am I supposed to do? Maximum volume of such a box. So xyz is the volume, and so method of Lagrange multipliers, you do the algebra, and it gets you solutions that have x and y both be 2, because we need positive solutions, right? We're looking for dimensions of a physical box. So yeah, so not surprisingly, the solution is the one that has symmetry. It has the you know, the bottom being a square, and then so it's a 2 by 2 by 1 box, and 4 cubed is the maximum. 4 cubic feet is the maximum volume. Here is objective function xy, and the constraint is an ellipse. Very similar to examples we looked at earlier, but I'll let you look at it. I mean, it's pretty, you can see it. You can actually draw this one by hand. It's kind of cool. And then finally, the section, this section ends with a rather theoretical problem. And so what I do at the end of this section is to ask the question, you know, suppose you've got an arbitrary quadratic form, right? An arbitrary quadratic form in 2 variables. So essentially you can capture that by a, b, and c. Right, here it is. ax squared plus bxy plus cy squared. And my question then is, determine formulas for the extrema of q on a circle of radius r given by x squared plus y squared equals to r squared. And what I do over the next about 2 pages or so is I apply the method of the, first of all, I can be sure by the extreme value theorem that solutions exist, right? Minimum, maximum. So I know the method's gonna work here because these are also smooth functions and you differentiate them all you like. And so I go through the method of the Lagrange multipliers, I solve the equations, and I deal with you know, some of the algebra here, and after a bit I get, you know, the values of the lambda, and so I work through some cases, and what do I come to? Eventually I come to the conclusion that the, you know, the extremal values are attained at x equal to that or y equal to that, and if you plug those in to the formula for the quadratic form, you get this. But the thing is, it's beautiful in that it's not just that. That simplifies down, 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 down to this, just lambda r squared. So in other words, the Lagrange multiplier for this problem is what's called the, it turns out it's the eigenvalue for the quadratic form here. So that's kind of neat, and ultimately just gives us this theorem, which is that if we want to have if we have a quadratic form and we want to maximize it or minimize it on a circle, we can calculate these lambdas, which I had formulas for on the previous page, and if lambda is the solution to the characteristic equation, then we can analyze those to decide where the minimums and maximums are, and basically here's the case-wise analysis that you get. If they're both positive, then if you look at the graph z equals q of xy, it's a paraboloid which opens up. If both the eigenvalues, or the characteristic values you call them, are negative, it's a paraboloid which opens down, and so z has a maximum value at 0, has a minimum value in the other case. If one is positive and one is negative, then it's like a hyperbolic paraboloid. It opens both up and down, and so it's neither max nor min. It's like what you call a saddle. And then if lambda 1 is 0 and lambda 2 is positive, then it's like a parabolic trough, which opens upward, and if it's one is 0 and the other one's negative, then it's parabolic trough, which opens down. And so this is kind of neat, because in the next section, basically, when we look at, if I recall correctly, next we do, multivariate Taylor series, we'll learn that you can expand a function in terms of a constant piece. Well, the linearization is what we called it before. So you can expand a function as linearization plus what's called the Hessian. And the Hessian is a quadratic form. And so if we're looking at a function 2 variables, we can decide how that quadratic form piece is going to behave by just looking at its characteristic values. And it turns out when you actually sort through what this means in terms of second derivatives, it gives you the second derivative test. And then, like, you know, in more generality, you don't just have a quadratic in 2 variables. You have a quadratic in n variables, and then you need linear algebra to sort through it. But anyway, more on that later, I think. So I'm going to stop here for this one, and we'll pick up with multivariate Taylor series in the next one. Thanks.